Hello Year 12. We're going to learn today about small angle approximations. So as a quick recap, I want you to have a think about in radians, what are the answers, what are the formulas for working out the area of a sector, the arc length and area of a segment. Just pause the video, see if you can write them down. Okay, so the area of a sector should have got half r squared theta, arc length is r theta, and area of a segment is a half r squared theta minus sine theta. Hopefully you remember those from when we did those in school. Okay, so we're going to have a look at some different graphs now. Here is a graph of tan x. As you can see, this is on radians on the x-axis. So this is pi and this is 2 pi. If I put the sine graph on it as well, you should be able to see that then that goes from 0, then it goes to pi, then it goes to 2 pi as well. And I'm going to put on the graph of y equals x. So as you see, we've got three completely different lines here. Now, we're going to focus in on when we've got a small angle. So if I zoom in here, you should be able to see something quite interesting, that at very, very small angles, the three lines are on top of each other. They're all equal to each other. So here's it zoomed in. So we've got tan x, and we've got y equals x, and we've got y equals sine x. So from these three graphs, we should be able to say that as long as we're using radians, when we're using small values of x or theta, then we should be able to see that sine theta is the same as theta, and also tan theta is the same as theta, but only in this very small angles here. If we go back to Desmos, and I change my settings and put this into degrees, as you can see, the three lines are not on top of each other anymore. So if I zoom out, I'd have to change the settings to be able to see them all properly. But as you can see, here's our sine curve, and here's our tan curve, and you can see that it doesn't hold for when we're using degrees, only for radians. Okay, so if x was in degrees, we cannot see this case. Okay, we're going to look at how to use this then, and why is this important. So PT is a tangent to a circle here, and it's got a radius of r. The circle has a radius of r. So here's the circle is the red curve, and it's got a centre O. So how long is PT? Well, if you've got a triangle here from OP to T, we know OP and we know theta. So if you use SOHCAHTOA, you can work out that PT is r tan theta. The area of the sector we know is a half r squared theta. That is always the case for a sector. And we've got r and r here and theta, so half r squared theta. The area of the triangle OPQ, okay, so it's very similar to the sector, but it's got a slight difference here. Well, area of a triangle is a half AB sine C, so in this case we would get a half r squared sine theta. And the area of the triangle OPT, this triangle here, the blue triangle, is base times height over 2. So that would be r squared tan theta halved. Now, if we make that triangle very small, if we make theta very small, the smaller we make it, the closer you can see these three areas are going to be to each other. So when theta is very small, these three areas are very close in size. So a half r squared theta is approximately the same as a half r squared sine theta, which is approximately the same as a half r squared tan theta. Now I want to think about using cos instead of sine and tan. So we're going to look at a circle again, this is a unit circle, which means it's got a radius of 1. So find the different lengths. See if you can work those out, pause the video, have a go, and then restart it when you think you want the answers. Okay, so the length QR, so this length here, well, if we know this is 1, then we can use SOHCAHTOA and work this out as sine theta. OR, again, the same principle, we can work this out as cos theta. PR here, well, this is a length of 1. This is the radius of the circle. This is also the radius of the circle, OP. So that's 1 minus cos theta. And then QP is the curved section here. And because we know that arc length is r theta, and r in this case is 1, then QP, the arc length QP, it will be theta. Okay, so we can now think about using, when we've got a small angle, using Pythagoras. So when theta is small, PQR is essentially a right angle triangle. So this section here, so these two, as the angle gets smaller, this green line and this red line will get closer and closer together. And we know that this length, the arc length is theta, and we know that this RP was 1 minus cos theta, and we know QR was sine theta. We just worked all of those out. So we can use Pythagoras on this triangle here. So we know that PQ squared here is the same as RP squared plus RQ squared, so on the right angle triangle, which gives us theta squared equals 1 minus cos theta all squared plus sine squared theta. Expand out our bracket, so theta squared equals 1 minus 2 cos theta plus cos squared theta plus sine squared theta. Now we should all recognise that cos squared theta plus sine squared theta, should know that as an identity, so that equals 1. So if we replace that with 1, we've got 1 minus 2 cos theta plus 1, which is the same as 2 minus 2 cos theta. Now if we can rearrange this, we get add 2 cos theta to this side, subtract theta squared, so then we can work out cos theta is 2 minus theta squared over 2, or it can be written as 1 minus theta squared over 2. So this is when we've got a small angle, and then this is our cos approximation. So here are the 3 small angle approximations. Sine theta is approximately equal to theta, tan theta is approximately equal to theta, and cos theta is approximately 1 minus theta squared over 2. All these approximations are very good for when theta is between negative 0.1 and 0.1 radians, and you get given them in the formula book. So you don't need to remember them, but you do need to be able to use them. Okay, so let's have a go at some examples. When theta is small, find the approximate value of sine 2 theta plus tan theta all over 2 theta. Now, this is the key thing here, that theta is small. You're told it's small, so that's when you need to recognise that this will be a small angle approximation question. And then in part B is cos 4 theta minus 1 over theta sine 2 theta. Have a go and then come back, press play again when you want to have a look at the answers. Okay, so if we use our small angle approximations for sine and tan, then we know that sine 2 theta would go to 2 theta and tan theta would go to theta, and then we divide it by 2 theta. So this gives us 3 theta over 2 theta, which is 3 over 2. For part B, cos 4 theta, we would need to rewrite this as 1 minus 4 theta squared over 2. And then we take away 1. And then theta, sine 2 theta, we can replace with 2 theta. 1 minus 1 is 0. So we've got minus 4 theta squared over 2, which gives us 16 theta squared over 2. 1 minus 1 cancels out. Minus 8 theta squared over 2 theta squared, and then we divide that, cancel out the theta squared, and we get negative 4. Okay. Find an approximation for cos theta minus cos 2 theta when theta and 2 theta are both small. Hence, find the value of cos theta minus cos 2 theta over theta squared as theta is approaching 0. So this means when we have a small angle. Press play when you want to resume the video. Okay, so Find an approximation for cos theta minus cos 2 theta. Well, this is 1 minus theta squared over 2. Take away 1 minus 2 theta squared over 2. So that's 1 take away 1, which is 0. And then we've got negative theta squared plus 4 theta squared over 2, all over 2, which gives you 3 theta squared over 2. So this is the top part of this equation here. Cos theta, this expression, sorry, cos theta minus cos 2 theta. So if we then want to divide that by theta squared, we would get 3 over 2 as our final answer. Okay, so for today's work, I'd like you to go to the A2 book and you're going to do exercise 2.3, which is page 24. Thank you for listening.